Good morning, everybody. The Goodby 2020 Codeforces contest has just happened. So if you competed in that, hopefully you did well. Congratulations if you did. Good luck, have fun upsolving if you didn't. And either way, this video is going to have solutions to the problems that I know how to solve. So I was a tester for this round, which means I wasn't able to compete in it, obviously, because I had seen the problems before, so it wouldn't be fair. But I helped test to make sure none of the problems were like blatantly broken, and I was able to solve problems A through F. So here's what the tester's scoreboard looked like. This was the virtual participation round that we did. Yeah, so I got problems A through F, and those all worked well enough. They were pretty much the difficulty that expected, but I'll comment on the difficulty in a moment. And none of the testers solved G through H in their virtual participation of the round. I think Anton was the highest rated tester that we had. He's 2,800, and then this guy is 2,400. Yeah, so it's about as expected, I guess. An international grandmaster shouldn't solve the set, otherwise that probably means it's too easy for like people like tourist. Yeah, but otherwise it looks good. My personal opinion on the problems were that I don't want to share this kind of stuff before contest because like it might spoil things, right? So I'm saving it for this. My personal opinion was I thought the biggest thing, and I think this is going to be the biggest complaint, and I told the author about this, but these the first paragraphs that are just stories, people don't really like that, and they're not like italicized or smaller. If you want stories, like, that's fine. If you want just backstories to make the problems interesting, that's fine. But do it kind of like how Monogon did it, where they're smaller, they're like out of the way. Where if you want to just skip to the problem, you can do it, right? You can just start doing this if you want. And for instance, like these first two paragraphs they're almost entirely just, you can skip them. Other than this line right here, the entire first two paragraphs aren't necessary to solving the problem. And they're all like that, right? So I would move this away. That's the biggest criticism that I have across problems. Also, I really did not like problem H. I thought problem H was very difficult to understand. It's possible it's been updated a little bit. I haven't really had a chance to check too thoroughly, but yeah, problem H was very confusing when I first read it. So I gave some feedback for that as well. I didn't have any particular issues with any of the other problems though. It was just problem H that I had a very difficult time understanding. There were some small typos, but other than that, it was pretty good. All right, so that's my brief rundown of the set. Let's jump into what the problems are and their solutions. For problem A, you have we'll open up a whiteboard here so we can talk about it and draw. You have a bunch of trees that are planted on some number line. So if your number line looks like this, maybe. You've got a tree here, and then a tree here, and maybe you've got several trees on this number line, like this maybe. You want to see how many different areas can you get if you connect this tree to two other trees on the bottom. So for instance, you might connect these three trees here. I'll put labels on the positions, so 1, 2, 3, and 4 maybe, or 0, 1, 3, and 4. So if you make this triangle has area 1/2 base times height. So the base is 3, the height is 1. So the area of this triangle will be 3 times 1 over 2. That's equal to 1.5. So you can get an area of 1.5. You can also get an area of 0.5, like this. So you can get 0.5. And you can also get an area of 2. So you could get a triangle that looks like this. So you can get 2.0 as well. I think that's all of the values you can get for this. So if we erase these, you can get 1.5, 0.5, and 2. But yeah, like if you look at this, I guess this is 1. So you can get 0.5, you can get 1, 1.5, and 2. And those are all of your choices. So there are 4 different possible areas you can get for this problem in this particular case, and you just want to print how many there are. So yeah, okay, it's pretty much the same as the first sample, so we're good there. How do you solve this problem? Well, this height is fixed. It's always going to be equal to 1, so we don't need to worry about that. The part we do need to consider is what are the different values for the different bases that you can get. So basically, we want to calculate how many different differences are there, and we can look through every pair and add that difference to some sort of set. So either a hash set or a tree set maybe. Here's what the code looks like for that. So the array is very small, so I can safely sort it. So I sort this array here. And after that, I go through, I just do an n squared loop, and then I add all of these differences to some hash set. The number of things there are is the total number of different values that exist. If you're not familiar with using hash sets, you could use arrays as well. That would solve them just as well. Okay, that's problem A. Problem B, last minute enhancements. So in this problem, you're given some array, basically size 10 to the 5th, and for every element in the array, you can add either 1 or 0 to that element, and you want to make the array contain as many unique elements as possible. You're also given this nice constraint, which is the values in the array are given in increasing order. So you don't have to worry about sorting it. You don't have to worry about getting caught with a Java arrays.sort being n squared. And I don't think I even noticed this part of the problem when I solved it, or maybe it was changed after, I'm not sure. But yeah, so this sorting part is not particularly important. How do you solve it? So basically the observation is like, if we go through the numbers in increasing order, we can use a greedy strategy. Because if we're considering some number here, and we've got a bunch of numbers before us, we already know what all of these numbers are. For the numbers after us, these are all going to be greater than or equal to whatever this value is initially. So the observation is, if we can keep this element as what it is now, that will have it will interfere with these future numbers less. And you can do an exchange argument to show that in any case where you can leave this the same, some optimal solution lets this leave us the same. There's one caveat there, which is we don't want to leave it the same if we've already seen that number. So if this was a 3 here, and this is initially a 3, we definitely want to make this a 4. It might not do anything as a 4, but it definitely isn't any helpful, or it's not helping us at all when it's a 3. So we might make this a 4. Then later on, if we see another 4 here, then we might be able to make this a 5. So yeah, that's the reasoning behind that. And that's the idea. We go from smallest to biggest. If we haven't seen some number before, we leave it as what it is, otherwise we increment it. My implementation for this is a little bit messier than it needs to be, because I guess I did see that it was sorted, so I used that obviously. But for each element in this array here, I see if the set contains it. If it does, I add one more than it. If it doesn't contain it, then I add this element. At the end, just the size of the set is the number of, I guess, the diversity of the modified array, which is what you're going for. Okay, awesome. That's problem B. Problem C, canine poetry. So in this problem, you are given some string, and you can modify any character in this string. And you want to do that so that all palindromes in this string are size 1 after you do these modifications. Let's do some example. So in this first character, or first line, we have string BABBA. There are a couple palindromes initially. We have this palindrome of length 2, we have this palindrome of length 4, and we have this palindrome of length 3. Let's look at the palindrome of length 4, for instance. What we can notice is this palindrome of length 4, anytime we have something like that, it'll have a palindrome of length 2 between it. And if you have a palindrome of length 5, for instance, that means these match and these match. We know we've got a palindrome of length 3 within it as well. So if we remove all palindromes of length 2 and of length 3, that will guarantee that our string will have no palindromes in it. Because any palindrome bigger than length 3 will have either a palindrome of length 2 in it or a palindrome of length 3 right in the middle. So that's what we're going to do. Only consider palindromes of length 2 and 3. So, how do we do this? Okay, so let's say we've got some character here. We've seen it, maybe we know it's an A. Now we've got this character here, and this is like some B. This B has a couple things that it can't be. We don't know what this next character is going to wind up being because we might change it. But we're going to change this B to something that is not helpful at all, right? Maybe we'll change it to a Z, maybe we'll change it to something else. We don't want it to match the A. We also don't want it to match this. And we also don't want it to match the thing that's 2 before it or the thing that's 2 after it. Because we don't, this could be a palindrome of 3, and this could also be a palindrome of 3. We want to eliminate all of those palindromes. So if we know we're going to change this B, there are at most 1, 2, 3, 4 different letters that we don't want it to be. Since the alphabet has more than 5 letters, we'll be able to find something, right? If we fix everything else, we can make this B something that doesn't conflict with any of those 4 choices. We've got another 22 letters to pick from. Just pick any of them. So what I do is I set it to like some like garbage character, right? So I set it to like an @ symbol, I think. And this just indicates like it's going to be something that's different from everything else of these 4 positions. So you don't need to worry about it. After that, I have basically just very simply all I need to do is for each character that I'm looking at, if I'm looking at some character here, I look at the 2 characters behind it, and it can't match this, because if it does, then we have a palindrome of length 2, and it can't match this first character, because then we would have a palindrome of length 3. So if these get turned to ats, we know we don't, like, this check is going to be false, so we don't have to worry about it. But if it's not an at, then, and these match, then we want to modify one of these 2 characters. Now, we could, like, yeah, there are a couple ways we could do this. We could modify this, or we could modify this. Those are the 2 options. So, yeah, what's the solution there? Suppose you have like a Z here, and then you also have a Z here, and these match. You might be worried if we always replace this character with an @ rather than replacing this character, that we might incur a palindrome here, and then we might also have to replace this character. So you might think, well, maybe we want to replace this one. Maybe we're not sure. It turns out you can always just replace this right character, because if these are the same, the only reason that you would have a palindrome here is if this is also a Z. So in this case, you're going to have to remove both of these anyway. So yeah, you just always want to remove the rightmost character. If there are 3, then like this element isn't relevant, because no matter what it is, it's going to be the middle of some palindrome of like 3. So you want to remove the first and the last element in this case. Or like first or the last, but the last because everything to your left is processed. Okay, hopefully that made sense. In code, it's actually very simple to code. The idea is we just have this character array of everything in the string, and then we go through each character. We start at character 1, index 1, and if this is the same as the thing before us, we set us to an @ symbol, and then we increment the count. Also, if the thing 2 before us is the same as what we are, then we increment the count, and we set what we are to an @ symbol. And the number of things we've changed to @ symbols is just the answer, right? Everything that we need to change to something else, that's one operation. We want to minimize that. So that's the solution to problem C. I guess that took a little bit longer to explain than I would like, but yeah, hopefully that's fine. Okay, problem D, 13th labor of Hercules. So we have this kind of off-the-wall task, but basically you have a problem statement as well. So in the problem statement, you've got a tree with n vertices. We should know what a tree is here. And you want to make a K coloring for a bunch of different k values. So you want to like do a 1 coloring of the tree, a 2 coloring of the tree, 3 coloring, etc., all the way up to n-1 coloring. K is the maximum number of colors you can use, and you want to color each of the edges so that every edge has 1 color assigned to it. And now this part is where it gets kind of confusing. You only look at connected subgraphs where like the entire group is connected. Let me give an example. If you're not familiar with this, it might be a bit confusing. So suppose you have a tree that looks like this, and these, you color both of these 1 color, and you color both of these 1 color. So we're going to take the sum for each of the edges, or for each color, basically. So for red, we have 2 connected subgraphs. We take the maximum of these 2, which, let's say, let's give some values to these. 3, 5, 7, 1, and 2. So the value of this will be 8. The value of this will also be 8. So we take 8 points for red, and then for blue, we have 1 connected subgraph, which is this right here. The value of this is 2 plus 5 plus 7, which is 7 plus 7, which is 14. So 14 for blue. So the total value of this coloring is 8 plus 14, which is 22. Okay, you can do better here. The thing to notice is that you don't want to ever separate colors like this, because we just threw away this node here, right? We didn't actually use it because we didn't use this coloring since we maximized it, which means each color of edges needs to be some continuous subgraph. Otherwise, you're wasting stuff. So if we color this in, now we use this 1 node, and before we weren't using it at all. So that would make this 15, and that would make this 23. So that's some improvement. Okay, so that's the main observation. The only thing after that is that we should look at like these nodes, and sometimes you can double count a node. That's like the other thing to keep in mind. So in this case, if we color this blue, this red, and this green, then this node here gets counted for blue, red, and green. It gets triple counted. Which means that we might want to do this if we have more colors. Ultimately, what we can do is just say every time we add a new color, we get to pick where we cut the tree so that this part of the tree is whatever that color used to be. So we get to make a new cut to the tree every time we add a new color. And every time we make this new cut, the only thing that changes is we get to add the value of 1 more node. We can also only add the value of some nodes. In particular, a node can only be counted like what its total degree is in the given tree. So that's the idea. We have a limited number of times we can add each node. That's equal to the degree. And we start with adding each node once. Every time we add an additional color, we get to pick 1 more node from this list of nodes we can add, as long as we can still add that node. And we add that node's value to our total. And that's the solution to the problem. What does the code look like? It's pretty simple. I don't actually build this graph since you don't need it. I just have a priority queue for each of these values. And the value is just like the value of some given node. So we're given the values of each node in input. And I want to store whether or not some node has been used at least once before, or some edge has been used once before. Because like initially, if a node has degree 3, then you can add it 2 additional times. So those 2 things will be what's in my priority queue. Alternatively, you don't need this, and you can just remove the first n things from your priority queue, or like the first n values from the beginning, because everything counts once. So maybe that's easier, I'm not really sure. But yeah, okay, so I read this edge, and if this edge has already been counted once before, then I add it to the priority queue. Same thing with the other node and the edge. Pretty simple. The reason this is negative is because I want my priority queue to remove the biggest things first, And in Java, by default, priority queues remove the smallest things first. In C++, they remove the biggest things first. So in C++, you wouldn't need this to be negative. You just have it positive. It would give you what you want. And then I also invert it at the end. Okay. So then, yeah, n minus, like, initially the answer is just the sum of all node values, and then you just take the biggest thing from your priority queue each time. And that's the idea. Should run fast enough. And log n solution. Very good. Okay. That's problem D. Oops. Let's get problem E real quick. So in this problem, you have some sequence of integers which might contain duplicates, and you want to know, like, you want to iterate through all first elements, then all second elements, and all third elements, and you want the and of the first and second elements times the or of the last two elements. You want to know what the total value of this is, and then you print it under mod, because this could be very big. It could be approximately order n cubed, or order max value cubed, and the values can go up to 10 to the 18. So this could be like 10 to the 18 times 3, which could be a pretty big number. So that's why you've got some mod. Your mod is 10 to the 9th plus 7. All right, so what are our observations here? Let's look at this equation for a minute. Think about it. So what we can notice is, suppose we know what this x sub j is. This is the tricky thing. The x sub j is tricky because it's in both the left half and the right half. But if you imagine that you know what the x sub j is, then we're going to end up brute forcing what this x sub j is, but then we've got this x sub I that we're going to AND it with. So we've got some number. We're going to take for each element in the array, we're going to AND it with this number. Now, this thing is going to get multiplied by a bunch of other things. But really, each of these, we can find what the total value is, and then just multiply the total by these. So I guess it's we can do this mathematically, but the idea is these two things are separate. We don't need to worry about doing one iteration here. We can just worry about doing the iteration here. Okay, so let's do the math, because some people like math, so we'll do it like this. So initially the formula we're given is the sum from I equals 1 to n, j equals 1 to n, k equals 1 to n of xi and xj times xj or xk. So the order of these loops doesn't matter. We're going to iterate through all of them anyway, so the order is fine. So what we can say is we can move this outside, right? So instead of ijk, we can do j and then ik. Now the next thing to notice here is that this part doesn't depend on k, and this part doesn't depend on I. So really what this is the sum from j equals 1 to n of one thing times another thing. So this is the sum from I equals 1 to n of xi and xj times this is the sum from k equals 1 to n of xj or xk. Hopefully that makes sense. So now what this problem has reduced to is we need to somehow, in some fast way, evaluate what this is. So we need to say, for some element, we're going to brute force this part. This loop is going to be very difficult because it's messy. It's in both places. So we're actually going to do this, but we need to very quickly evaluate what is this equal to for some value. Now, instead of worrying about this, you can do this mathematically, I guess, but here's how you can think about it. Instead of worrying about this for each element, we can worry about it for each bit. So in this case, here, what we have is we're only going to count bits that x sub j has on. So if x sub j is 1001, for instance, we only count this bit for, well, this is the bit for 1s, and this is the bit for 8s. So we count the 1s bit and the 8s bit. We want to see, for this 1s bit, how many other numbers have this 1s bit on. And that's going to be the number of times we add 1. We also want to see how many numbers have the 8s bit on. That's the number of times we add 8. So we can evaluate this in order number of bits, in order 60, instead of order number of elements, in order 10 to the 5th. Then we can do the same thing for this here. So this is like very similar, but slightly different. In other words, we're going to add, like for each of these things, we n times, let's use a different color here to be less confusing, n times, we do the following. So n times, usually we add whatever this thing is. So let's say we add ourselves. So we add x sub k. And then we also add everything else. So n times we add x sub k. We also add like the sum of all elements. But we've just overcounted here because we want to like subtract out the and, right? Minus the sum of the and. And the sum of the and we can calculate in the same way we did before. So you can clean this code up a little bit, seeing as how you've got like similarities here, or you can just like do it as you think about it. But basically it's not too difficult to come up with a solution, and your solution runs in n times 60, n times like log max value time. Here's kind of how it works. So I store, or here's the code I guess. I store the number of things that have each bit on. So I just iterate through everything in the array, and then I iterate through each bit, and then set this. Don't forget to use longs, I guess. That's a classic. Then I store all of the powers of 2 under mod. You have to be careful here, because if you multiply, you might overflow longs, so you just have to watch out there. Cool. And then I store the sum of everything under the mod, because we're using the sum of everything in our math. So then for each j here, this j represents the middle element, the x sub j. I calculate the sum of ands and then the sum of ors, and those get multiplied together at the end here under mod. So the sum of ands is very easy. I just iterate through each bit, and then for this element, if it has this bit on, then I include this bit. The number of times I include it is however many things have this bit. Ors is pretty similar. For each or, I kept, when I was doing this, I kept misspelling the ORS, like plural of or, as ORZ, because that's what everybody says. But anyway, yeah, this is pretty similar. It's just the same as the math that we talked about earlier. Initially, it's the sum of everything plus j times n, where j is this element and n is the number of things. But we just double counted that same thing, which is the sum of ands. So yeah, same thing. And that's the solution to problem E. Okay, the last problem that I solved was problem F, and then I won't talk about these because I don't really have solutions to them, to be honest. And I asked for solutions in order to explain them. I can understand if they don't want to give solutions ahead of time. That's totally understandable. Yeah, like you can only trust people so much, because like if you give them solutions, they could like leak them to someone, I guess, maybe, but I don't know. Like I could leak the problems to people too if I wanted to, so like yeah, I don't know. I guess maybe they trust their solutions are right. Hopefully they are. I don't want their round to go unrated. Anyway, last problem is problem F. Euclid's nightmare. I thought this was actually significantly easier than E, for me at least. But oh well. The idea is a bit complicated, but basically you have a bunch of vectors where each vector is basically a bunch of bits. So in other words, you have like a bunch of bit sets, and what you can do in a given step is XOR the 2 bit sets, and you can do that as many times as you want. Now obviously for a given bit set you only want to XOR it either 0 or once. If you XOR it like 2 times, it doesn't matter. The only thing that matters is how many times you XOR it mod 2. The question is, how many ways are there to get all of your vectors equal to 0? Oh wait, never mind. That's not the question. Just kidding. The question is, how many things can you reach? And how many of the vectors you're given actually matter? Yeah. So how many, if you can like XOR or not XOR every element, how many vectors can you reach in the end? And how many of the vectors that you're given actually matter? Those are the 2 questions. And also, I guess, which elements that you're given actually matter. Okay, so let's stop thinking about this in terms of linear algebra, because linear algebra is confusing and hard for humans to understand unless you're some genius like 300 IQ, and let's instead think about it as maybe some graph problem. So the important constraint here is that you have at most 2 bits equal to 1 in some given vector. So that's the important part. Let's look at each bit as a node. So what we have here is, like, imagine we've got this thing here. This is one vector. We've got some other vector that's like this. We have some third vector that's like this. And maybe we have a 4th vector that's like this. Then we can make nodes for each of these values. So we'll call this A, B, C, D, E, and F. And we can make an edge between these 2 if they have 2 1s with them. So we have an edge from A to D. We have an edge from D to E, from B to E, and from, this should be a B, and also from B to C. So in this case I have a rope, but it might be anything. It might be a graph, it might be a tree, it might be whatever. Depends on what these input values are. There are a couple other cases too. You might have, instead of this, you might have just like a 1 with a bunch of zeros. So in this case, node A is like special, because node A we can choose whether we want it to be, we can flip just node A. In all of these other cases, we flip both things on the edge, right? We include this and don't include this, or whatever. Like we flip whether we include A, and we also flip whether we include D. So here's the thing to notice, I guess, which is, if we pick any path, if we use any continuous path of edges, here we used this edge, and this edge. These 3 edges correspond to using this, and this vector. The XOR of these vectors, here we've used this edge twice, but these 2 once. In other words, if we look at this graph here, when we pick some path, every node is included on 2 edges in the path, except for the first and the last node on that path, which are included once. So for any 2 nodes that are in the same connected component in this graph, we can flip both of them. Now the question is, right, let's say we have everything initially unmarked. We can mark any pair, or we can flip the markings on any pair. So we can do that. Now maybe we could flip C and then flip E. So we could undo C and then do E. And then maybe we could mark both B and A, for instance. So the question is, what sets can we have marked in this group? Well, initially, if we ignore this last thing, if we don't have any special nodes in this connected component, then all that matters is like the connected component. And if we ignore, like, let's say we have one special node here, or one node that we'll like put off to the side. For the rest of these, we can choose whether we want them to be set or not. If we need to change them, then we'll choose the path from the special node to that. So if we want A to be marked, we'll choose A to C. If we want D to be marked, we'll choose D to C. And we can keep doing that. So for every node in the tree, other than this last one, we can set what it needs to be. For this last node, it's forced. right? We can't change it because in order to change this, we would have to pick some other node and we would mess up what it is. So the number of ways of doing this is 2 to the n minus 1, where there are n nodes in this component. Now it's slightly different if this is like a special component. If it's special, then, or if there's a special node in the component, for instance, let's say this e is special, then we want to include this e because we could make this the last component, or yeah, we can make the e the last component because we can flip the e by itself, right? So that would correspond to having this vector here that only has 1, 1. Now this e is special, so we want to be able to flip the e by itself, and if we do that, then we have just 2 to the n. We have a special node here. So when do things matter? Anytime we add an edge that connects to components, that almost always matters. There's one caveat there, which is if we add an edge, let's say we have something like this and we have something like this, and we can initially like change this node here, we can change this node here. If we add this edge doesn't actually affect our solutions because this whole thing is free to change however it needs to, and so is this connecting component. So in this case, this edge doesn't matter because it's connecting two totally free components. If one of these isn't free, then this has like the degrees of freedom in this is just 1. The degrees of freedom of this is 2. So if we add this edge, we increase the degrees of freedom. Now you can just worry about this on its own using some disjoint set magic, but there's actually a really clean way of coding it. And what that is we can add an extra imaginary node. And instead of, when we have this special node, what we can do is add an edge to this imaginary node instead. So this is like, this doesn't actually exist, but it represents whether some component is like free to change or not. Like we can flip every node in the, we can like, whether the component has n degrees of freedom or n minus 1. So if it has n degrees of freedom, it'll be connected to this magic node. And now if we have that, then every time we have some edge that just modifies one node, instead of doing something special to the components, we can just connect to the component to this special node, which represents that. Now, every component here, the number of degrees of freedom it has is just 2 to the n minus 1. So this here, this is the real component, what I've circled. That is the component we're considering, and it has 2 degrees of freedom, which corresponds to this thing here having 2 degrees of freedom because it has 3 nodes and we're taking 2 to the n minus 1. Okay, that's the idea. Every time we add an edge, it increases our degrees of freedom by a factor of 2. So all that matters is how many factors of 2 have we added. And in that case, this first number, you might have noticed it from samples, but the first number you print is always going to be 2 to the second number. And then this is just the edges that you add. So let's go through the code for that real quick because it's just so clean. You copy and paste a disjoint set, and that's pretty easy. But other than that, you just look through each of the edges, and either it's 1 element or it's 2. If it's 1, then I just made my nth node this special node. So uniting n with n minus 1, if this adds a new edge to the tree, that means we've added a significant degree of freedom. If it doesn't add an edge to the tree, that means these two things were already connected, which means we didn't add any new paths. So there are no new things that we can change that matter. The other case is this case right here, where the 2 nodes we're given are both real nodes, right? There's no like imaginary node in this case. So in this case, if this adds an edge to the minimum spanning tree, or to like some spanning tree, then we increment our answer as well, and then we add one more element here. Now this, you could do better. You can just do powers of 2 stuff for this. I didn't make that observation in contest, So you can clean this up quite a bit. You don't need to do this actually. You can just like calculate 2 to the power of whatever under mod. You can just even do slow exponentiation because it'll be about 2 to the n. So you can just calculate that once very slowly. And yeah, that's the goal here. So here's where I calculated actually. But the result is just like this exponent, which I go through all of this work of calculating, is really just ant stat size. Cool. And yeah, that's the solution. Then you just print it out. Make sure you use print writer for this because there can be a very big answer. But that's the idea. So hopefully you enjoyed the contest. Hopefully the solutions were helpful. That is all from me. I don't know how to do these last 3 problems. And I haven't heard if there's going to be an editorial for them. I would think so, but I don't know. I can't promise anything. So, yeah, good luck. Hopefully you enjoyed the contest and the year. And have a great 2021. Goodbye.